Hello everyone, today I'm going to talk about motion of a disk, the acceleration analysis. So I talked about the motion of a disk, the velocity analysis. We had 5 different types of motion, but in this video I'm going to talk about acceleration analysis. So whenever we talk about acceleration, that means that we have to deal with kinetics rather than kinematics. So let's think of, we have a disk. A moment is being applied to our disk. The center of gravity, I call it G, that would be the center of the disk, and the point of contact would be C. So if I draw the free body diagram, of course I have my moment M, I have the weight, mg, I have N, the normal force, it should be the same as mg, and then I have the friction force. If it is pure rolling. And I have to draw the kinetic diagram. I have Ig alpha, MAG. So if it is pure rolling, then Ag would be R alpha. And we can get to this conclusion if we write our relative acceleration equation, AC plus Ag with respect to C. What is acceleration at this point? Remember, it's not zero. We are not talking about velocity. We are talking about acceleration. Acceleration has 2 components. The tangential component is 0, but the normal component is not. This point is rotating about the center. So it has an acceleration towards the center, the normal component, which is r omega squared. And if I want to write it in a vector format, it would be J, positive J means towards the center. Then Ag with respect to C has 2 components, the tangential component and also has the normal component. So these 2 cancel out. That's why Ag would be R alpha. But let's get back to our kinetics diagram, to our free body diagram. So the magnitude of the friction force, if it's rolling or if it is static, is less than USN. That's for rolling, because rolling is also with a static friction. And if it is sliding, then the friction force would be mu n. So we need to remember that mu n would be the maximum value of a friction in case of rolling. So let's write our kinetic equation. Summation of moment about point C would be IC alpha. If we look at our free body diagram, the only moment that we have is the moment, the external moment that is being applied on our disk, and I would be 3m r squared alpha. Therefore, alpha would be 2m 3m r squared. So summation of forces would be the next equation that I need to write, would be MAG. So here the only force that I have in x direction would be the friction force. So the friction force is the force that is creating the acceleration for me. Now, if I write the acceleration, the maximum value would be mu n, and n here is mg, MAG. That means that the acceleration that I can have, if I cross out m, would be mu g. So that's the maximum acceleration that I can have with the given static friction. So if R alpha, here is R alpha, R times this magnitude, it should be 2m over 3mr. So our R alpha would be 2m 3mr. I have to compare it with Ag, which is less than mu sg. So comparing the two, that tells me if the R alpha is equal or less than mu SG, then I have rolling. But if R alpha is bigger than AG, then my acceleration cannot, the friction force cannot provide that acceleration. The power of friction force at most is mu G. If R alpha is bigger than mu G, that means that I'm going to have some sliding, so rolling with slipping. So we need to remember this equation tells us the maximum value of acceleration we can have, because that's the maximum value of friction force that we can have. Now let's look at another problem. Let's say we have our disk, but here instead of a moment, a force is being applied at the center of the disk. Again, we have our mg, and the direction of friction force, I really can't judge it before solving it. So I'm going to draw the friction force on both sides and then identify what would be the direction of friction force. If I write my kinetic diagrams, I have MAG. That's the point of contact. So summation of forces, summation of moment above this point will get rid of all the moment of all forces, the force friction, the force mass, and also the normal force. So I write summation of moments about point C. That gives me IC alpha. The only force that creates a moment would be my force F, the external force being applied at the system. So I can find my alpha here to be 2/3 of FMR. Also, I can write force equation on x direction or tangential direction would give me MAG E. So I have the force. Here it's interesting because I don't know the direction of friction force yet, so I'm going to write plus minus. The friction force would be mu N. So N would be mg here, plus ma, or a of g. So ag would simply be f over m plus minus mu g. In case of rolling, ag should be equal to r alpha. Let's write it here and compare the two. Ag is this value, and r alpha is 2/3 of f over m. I need to compare the two values. Let me erase this here. If I compare the two values, this is 2/3 of f over m, here f over m. So that means that if I want to have rolling, if I want ag to be the same as r alpha, then the friction force has to be negative. So Fm should be subtracted from mu g, so I get 2/3 Fm. That means that the friction force is to the left. So friction force is a negative value, or to the left. So here, in case of rolling, the friction force is acting to the left based on the two equations that I developed. So when force F is pulling the disk, so there is a tendency for point C to be moved to the right, therefore the friction force is resisting that to cause the rotation and rolling of the disk. If mu g is less than 1/3 of Fm, then we are going to have sliding to the right. So if mu g is less than 1/3 of Fm, what does that mean? So if mu g, if this component is less than 1/3 of Fm, which means that Ag is bigger than R alpha. That means that Ag is bigger than R alpha. So we have sliding to the right. So now let's look at another problem. Let's say we have an inclined surface with an angle theta. We have a disk with a radius of r, mass of m, going down the inclined surface. So I want to draw the free body diagram. This is mg. This angle would be theta. So I have mg sine theta, and here would be mg cosine theta. I have the reaction force N, which would be mg cosine theta. If I write summation of forces in N equals 0, there is no acceleration in N direction. And I have my kinetic diagrams, which would be Ig alpha, MAG. Alpha, I have the friction force. So again, I don't know the direction of friction force, so I'm going to draw in both directions, call them force of friction, F. So I need to write my equations now in 2D. I have 3 equations, so summation of forces in N gave me N equals mg cosine theta. Summation of moment about point C will give me IC alpha. About point C, I have only mg sine theta would be the tangential component times the radius will give me the moment. IC would be 3 half mr squared alpha. If I find alpha from this equation, I can cancel m, I can cancel r. So alpha would be 2g sine theta over 3r. Now let's look at the summation of forces. It will give me MAG. The forces that I have would be mg sine theta. Then that would be the friction force, which would be mu n. So mu n would be mg cosine theta. Because I don't know the direction of friction, so I'm going to write plus minus and then evaluate it later. MAG, the tangential component. So AG would be simply g sine theta plus minus mu g cosine theta. In case of rolling, AG has to be the same as R alpha. What is R alpha? 2/3 of g sine theta. So 2/3 of the first component of here. That means that this has to be negative. If we want the two to be the same, if we have rolling, that means that AG has to be the same as R alpha. Therefore, the friction force has to be going up or negative friction force. So for a disk that is rolling down an inclined surface, the friction force would be acting up. But now let's look at the problem and say that what if the disk is rolling up? Everything is the same, but the disk is rolling up. The kinetic diagram doesn't change. The free body diagram doesn't change. Still, the force of mass is acting here. The friction force, we can evaluate it, mg cosine theta, and here still we have acceleration. The acceleration would be the opposite direction of the motion, but still would be towards the the bottom of the incline, and none of our equation would change. So still the friction force would be acting up. So for a disc rolling on an inclined surface, regardless of the direction of rolling, whether it's rolling up or whether it's rolling down, the friction force is acting up. So that's an interesting finding for us. So let's see what happens if we have a positive sign here. So when we have a positive sign, that means that g sine theta plus mu g cosine theta means ag is bigger than r alpha. So ag is bigger than r alpha. This is not the first time that we see this. Ag is bigger than r alpha. But what does that mean for us? It means that the center of gravity has a higher acceleration than this point. And that means that we have a sliding. Then the friction force should be acting up, so it should be negative. So you can see we have a conflict here based on what the mathematics tells us and what the physics of the problem is telling us. So we can't accept that possibility. If Ag is bigger than R or alpha, the friction force has to be negative, and we are not going to get Ag bigger than R or alpha with a negative sign. So the positive component of our equation would not be physically possible. Now let's look at another example, but this time we have an inclined surface and a moment m is acting on our system. Everything is the same, it's just we have a moment. It's not just a pure rolling up and down. We have an external loading. So and we have mg sine theta here. We have mg cosine theta here. We have n. We have a friction force, could act up or down, kinetic diagram, Ig alpha, and MAG. If I set up my equation, summation of moment will give me IC alpha. So I have the external moment plus mg sine theta times r 3/2mr squared alpha. And summation of forces will give me MAG. The summation of forces is the same because the moment does not show up in the force equation. So I have plus minus mu g cosine theta. Will give me MAG. Now it's the time to compare AG and R alpha. So AG would be g sine theta plus minus mu g cosine theta. And R alpha would be 2/3 of g sine theta plus 2m 3mr. So let's compare the two. Here is a little bit more challenging because we have a moment m. So this tells us that if we can have a scenario that AG would be equal to R alpha if we want rolling, that means that we have to have the acceleration AG to be equal to R alpha. But R alpha, depending on the magnitude of m, we could have either positive or negative. So the friction force could be either going up or down depending on the magnitude of m. So there is a range of m that our disc would be rolling. And the friction force, depending on the magnitude of m, could be positive or negative. So let's think of it if m is a very small value. Let's say if m is very small, then of course that would be the negative sign. So it's going up, the friction force would be acting up. If m is a larger value, still to some extent, we could have rolling because we have a positive sign. But if m is too large, that even plus mu g cosine theta cannot provide that R alpha, then we are going to have some slipping. That means that R alpha, if M is too large, that means that R alpha is bigger than our acceleration, which means that we have slipping. And there is no scenario that we would have sliding. So that's interesting. If you're applying a moment here, there is a range of a moment that you could apply and you would have still perfect rolling. If you apply too much moment, then this would be rotating about its center and it would be rubbing against the ground, the inclined surface at this point. So for most of the problem with the disc, we really don't know what's going on with the direction of friction force. I don't want you to memorize anything. You can write it in both directions and set up your equation, and depending on what information we have. Sometimes we know it's rolling. Sometimes we don't know and we are trying to find it. So depending on what are unknowns and our unknowns, we can find the direction of the friction.